Yeah, so I think it might be time to start. So this is the second joint seminar of this term, I think the fourth one in history. We're very, very happy today to have Natasa Sesum, who'll speak about generalized cylinders as singularity models.
Thank you very much for the invitation. So it is my pleasure to be here. So here is the outline of the talk. First, I'm going to give you a brief introduction to the Ricci flow and the singularity formations in the flow. And then I want to talk about type 1 singularities of the flow, which I will define on one of the later slides. And basically, I want to go in two directions. The first part will be about formation of these type 1 singularities, which form at spatial infinities when you study complete non-compact Ricci flows. And then in the second part of the talk, I want to focus on compact Ricci flows. And I want to talk about formation of these generalized cylinders as singularity models. And in the last part of the talk, it will be again very related to the previous topics. I want to focus just on the round cylinders as a singularity models and talk about the asymptotics in that singularity formation. So here is the introduction. So let's say that you have like MNG, like a complete manifold, which is equipped with the smooth Riemannian metric. And then you start with that metric, and then you start flowing it with this Ricci flow equation, right? So where you flow the metric by d dt of g is negative to Ricci. Ricci is just the Ricci curvature. And that's like almost like heat flow type equation, because if you write it in harmonic coordinates, then the Ricci just becomes the Laplacian of the metric and plus some lower order terms. But of course, it's very misleading because these harmonic coordinates are first of all not preserved along the flow. So this just gives you some indication that it should behave very nicely and you should expect very nice regularity properties of the flow, which turned out to be the case. But I mean, of course, there is this concentration phenomenon caused by the reaction term. And if you, for example, look at the evolution of the scalar curvature, so R is just a scalar curvature, you can see that it is like the ddt of R is Laplacian R plus 2 Ricci squared. And then you can bound from below Ricci squared by R squared over N, right, where N is the dimension of your manifold, because the scalar curvature is just a trace of Ricci. And then you can see immediately from here that this R squared term should force this equation to blow up in finite time. And for example, indeed, if you start with a metric which has positive scalar curvature, then like the finite time singularity is inevitable. It always happens. But like in general, right? In general, let's say like even if you just evolve the full Riemannian curvature, it has the equation of this type. It is of this type, right? Where this last term is also quadratic in the Riemannian curvature. So of course you expect something bad to happen in finite time. And Hamilton proved that if you have the Ricci flow solution, there exists this time capital T, which is the maximal time of existence. And it's either infinity, or if it's less than infinity, then the norm of the Riemannian curvature has to blow up. And basically, I improved it that the norm of Riemannian you can replace by the norm of Ricci, right? So if the norm of Ricci blows up, then there is a finite time singularity. So how you deal with singularities? You parabolically rescale around those singularities, right? And you want to rescale in such a way that your sequence has uniformly bounded Riemannian curvatures. And then you want to take the limit of these rescalings. And this limit is called the singularity model. And these singularity models are usually ancient solutions, right? And these ancient, so this is singularity, right? Singularity models for Ricci flow, right? These are ancient, they're called ancient solutions. And these are just solutions that live from negative infinity up to some A, right? Where A is bigger than 0 and less or equal than plus infinity. Okay, so but there is a conjecture of Hamilton that most singularity models should be nicer than that, right? Not just ancient, but a little bit more special. And these are called the Ricci solitons, right? So what are those? So these are very special solutions to the Ricci flow. They're just moved by diffeomorphisms and homotheties. And the equation for the Ricci solitons is what I gave on the slide. So like the gradient Ricci soliton is the one that satisfies the equation Ricci curvature plus the Hessian of some function f, which is called the potential function, plus sigma, where sigma is just a number, times g is equal to 0. And if this sigma is less than 0, then you have shrinking solitons. If it's equal to 0, they're called steady. And if it's bigger than 0, they're called expanding. For us, these shrinking solitons will be important because shrinking solitons are the examples of those ancient solutions. They exist from negative infinity up to some finite time. And they are expected to mostly model the singularities in the Ricci flow. And
so could I ask, what does most mean here in the conjecture?
well, in some generic sense, that has to be defined. I'm like, so that is expected. I'm going to tell you later, right? That I'm going to come to that later, but it's right. That's why I put it in the quotation mark because it's not really still well defined, right? What I mean by that. But you should expect that. What I'm saying, like if you start flowing like the Ricci flow on some metric, what you expect that you reach type 1 singularity. Right, which is modeled on these shrinking solitons, right? So which means that if that's not the case, maybe you can perturb a little bit your original, right? And then flow it, and then you hit like you actually hit the singularity model, which is a gradient shrinking Ricci soliton. I mean, in that sense. And so these solitons can be viewed as generalizations of Einstein metrics. You can just take F to be constant, right? So you get Einstein metrics. Okay, so here is the definition of type 1 singularity. So let's say that, a g of t is the solution of your Ricci flow. And we say that the singularity at some finite time, capital T, is type 1 if, when you take the supremum of the norm of the Riemannian curvature and multiply it by the time to blow up, that is finite, right? So this means that the curvature at most can blow up like a constant over time to blow up. Right. So if that is not the case, if that quantity that we have here, is equal to infinity, then these are called type 2, right? And these are the ones that are not expected to happen, as I said, most of the times, right? So usually you expect these type 1 singularities to happen most of the times. And so how you study the singularities, you want to take a sequence of points on your manifold and Ti converging to the singular time, and you want to somehow rescale and then take the limit, right? So here is the definition of so-called essential blow-up sequence. So let's say that this sequence PI-TI, where Ti converges to capital T, we will call essential blow-up sequence if there exists some constant C, which is strictly positive, so that the norm of the Riemannian curvature measured with respect to metric x times Ti is greater than a constant over capital T minus Ti. And we call a point P to be a type 1 singular point if there exists this essential blow-up sequence that converges to that point on your manifold. And as I said earlier, this type 1, which we have on this slide, are conjecturally generic on compact manifolds. And the gradient shrinking Ricci solitons are like conjecturally generic singularity models, as I said earlier. And this is actually very true in a very precise form for so-called type 1 solutions, right? So let me just take that. So here is a theorem of Neighbor, and then later improved by Anders, Miller, and Topping, that if you have a type 1 solution, and remember type 1 solution just means that, so type 1 just means that for your solution, the Riemannian curvature T is bounded by some constant over time, right? So this means that you have a type 1 solution. So they said that if you have a type 1 solution and if X is a type 1 singular point in the like in the sense of the previous slide, then for any sequence lambda j going to infinity, if you parabolically rescale your solutions, right, by these lambda j's, then this subconverges to a non-trivial gradient shrinking soliton. So you see for these solutions that satisfy this assumption. Type 1 singularity is always what happens, and it is modeled by the gradient shrinking Ricci soliton. Right? So this theorem also applies in the non-compact complete setting as long as you have this type 1 singular point, right? As long as you can find this essential blob sequence that converges to something on your manifold, which is then called a type 1 singular point. So then you can still apply this theorem. And so Neighbor proved in the previous theorem the convergence to a gradient shrinking Ricci soliton, and Anders, Muller, and Hawking proved it. And actually, they saw that this soliton is non-trivial, so non-flat, because if you get just something Euclidean space in the limit, it doesn't tell you much about your singularity. So this is like what they did. Okay, so let me just tell you like the structures that we will be considering in the talk. They're called the multiply worked products. And we will use this structure to study both formation of singularities at spatial infinity and also formation of generalized cylinders as singularity models on our compact flows, right? So these are like, so B is our base, right? So, and it is n-dimensional. And then you have those fibers, which we call F1 up to Fa of dimensions at N1 up to Na, respectively. And these manifolds, F alpha, they are all Einstein with the Einstein constant mu alpha. And for us, mu alpha will be greater than 0, right? And here is just some notations, right? So our metric G on the total manifold M is given by this here, right? And then by G check, I'm just going to shortly denote the metric on the base. And G hat, GA is the fixed metric on the fiber. This is not evolving. This evolves, as you will see on the next slide. And by GA, I'm just going to denote this VS squared times the metric on the fiber, which is Einstein. This is just like the notation. And we will use Roman indices to denote curvature, to denote geometric quantities on the base, and Greek indices, alpha, beta, gamma, etc., to denote geometric quantities in each fiber, right? And there are A fiber, big A fiber, there are like A fibers that we have. And if you calculate the Riemannian curvature, it has basically 4 different flavors, right? So like in the first one that I wrote, all indices lie on the base, and then you just get back the curvature on the base. And then if you, if all fibers, alpha, beta, gamma, and delta are with respect to the same, right? If all these indices, alpha, beta, gamma, delta, come from the same fiber, then the curvature has this form, right? In terms of these working functions. And if you pair fiber with a different fiber, because we have multiple fibers, A of them, right? Then these curvatures look like this. So you have just the first derivative of V, and here we have the first derivative of V. And if we take 2 indices, I and L from the base and beta and gamma from one fiber, then you get the Hessian, where this check denotes the Hessian computed with respect to the metric on the base. And if you look at this, different components of the curvatures, and remember, like to control the Ricci flow, you need to control the norm of the Riemannian curvature. So here, like from here, you can easily. Okay, so from here, you can easily see that in order to control the norm of the Riemannian curvature, you need to control the norm of the Riemannian curvature on the base, and then these terms here, like the first derivative of V and also the Hessian of V, divided appropriately scaled. Okay, and so under the Ricci flow, this multiple worked structure is preserved. And here I wrote the equation, how these geometric quantities evolve along the Ricci flow. So G check is the metric on the base, and it evolves like this. So if you didn't have this last term, it would be just the Ricci flow on the base, right? But since it's a worked product metric, then you also get this extra term there. And each of the VAs, these working functions, and we have A of them, they evolve by this equation. So you just basically get a system that you need to consider. And there is and then with respect to this system, you have to, of course, compute the evolution of all geometric quantities, like the Riemannian curvature or the scalar curvature, etc. And then there is an easier way to do it, because you see, like in the evolution of G check, you have the Hessian of V, right? But you can actually introduce this vector field X, which is given like that. And then you can rewrite this equation, right, in this form, but this is just the Lie derivative of G check with respect to this vector field X. And then, so this means that if you just somehow erase this Lie derivative here, you will get the flow which is equivalent to the original Ricci flow after diffeomorphisms. So if we want to compute, let's say, the evolution of curvatures and so on, we can just like take this simpler equation, which involves just the first derivative of p. Okay, so this is a little bit about the structure. So let me tell you the first theorem, right, which is very much related to that theorem of Neighbor and Anders, Muller, and Topping. And this is a joint result with Carson, Eisenberg, Dan Knopf, and myself. And then we showed that if you take any p greater or equal than 0, we basically constructed a complete non-compact Ricci flow solution, mg of t, on R cross SP cross SP, where you can also replace this R by R to the k, that develops type 1 singularity, but at spatial infinity, right? And so this means that there is no type 1 singular point, right? Which was the assumption.
It's all at infinity.
At infinity, exactly. So you remember, if there is a type 1 special point, then the singularity models are always the shrinkers. So that's what their theorem says. But here we construct the flows where, right? So they develop singularities at spatial infinity. There are no type 1 singular points. And on each of these solutions, you can find this essential blow-up sequence along which you can rescale. And the blow-up limits like converge to a non-trivial gradient shrinking Ricci soliton. But at the same time, you can also find these, again, essential blow-up sequences along which no blow-up limit can be any Ricci soliton, right? So this means that, right, this is really crucial, what they say in their theorem, that this essential blow-up sequence has to converge to a point on your manifold, right? If that's not the case, then you can hook up an example where like these things can happen. And then we also give these criteria that like if you give me this essential blow-up sequence on these examples that we have, so the criteria that I wrote here, right, is the one that gives you that tells you whether your limit will be a soliton or not. If this ratio converges to 1, then we know that the blow-up limit will be a gradient shrinking Ricci soliton. If it's not 1, and you can find examples where it's not 1, then it's not. So this is what we did like a couple of years back.
Is it working?
It's okay, I'll try to and just do my computer. So like, and I showed to you like that to control the Riemannian curvature, you have to control the Riemannian curvature in the base, and basically the first derivatives of the working functions and the second derivatives of the working functions. And in order to do that, I don't want to go too much into details, but I'm gonna say that we needed this general non-compact maximum principle for systems like U, V, and W, where you can think of U as a non-known function that you want to control in terms of a V. Like you can have in your mind that you can take V to be U at at the initial time, but it may not be. And then W is somehow some bounded control function, could be anything, but in your mind you can just imagine that W is let's say a constant. And if we have like this U, V, and W satisfying this system of equation on our manifold, then we can prove suitable upper bounds on U over V for all times up to the flow exists in terms of this supremum of U over V at time 0 and our control function W. And right, so by using this general maximum principle, we can get all the curvature estimates that we want, and and use them to actually prove that like the set of initial metrics that we construct on our manifolds indeed behaves as I stated in theorem A. Okay. Okay, so we could also get something a little bit more from what we did in terms of the stability. But first of all, I want to mention the result of Golding and Minkowski, who considered generalized cylinders. So these generalized cylinders, Sk cross Rn minus k, these are the examples of shrinking solitons. Right? So they are all examples of shrinking solitons, and they showed that they are strongly rigid in the sense that if you have another shrinker which is close enough to this generalized cylinder on a large compact set, that it has to be isometric to it. So this is a very strong rigidity result. So you would somehow like assume that these singularities should be somehow stable. But here is what we can prove. So I'm going to first define the notion of weak stability. So if you have this solution G of the Ricci flow, we will say that it is weakly stable. If for this every epsilon, you can find delta bigger than 0, so that for any other Ricci flow solution, like for G tilde, which is at initial time delta close to my G of 0, to my metric G, then for all later times, right, the norm of the difference of these two metrics is less than epsilon for all times t greater or equal than 0 for which the flow exists. And now, like with this definition, like we can prove the corollary of our theorem A, that the Ricci flow of a direct product metric, G cylinder. What is G cylinder? This is just like a metric on our shrinker, Rk cross Sp, just generalized cylinder. That this is weakly stable, but with respect to some admissible perturbations. So we cannot just take any perturbations, but we have to take some perturbations that decay at spatial infinity. And then we can show that both flows, the cylindrical metric and the perturbed flow, that develop singularity at the same time, and they remain close to each other for all times after the flow exists. Of course, you would like to prove something more, and I'm now trying to contrast this to what we have in the mean curvature flow, where in the mean curvature flow, we happen to know more, and we have more results in the sense of this generosity, in the sense of stability and generic singularity models. And first, I'm going to mention the result of Dan Knopf and Gang Zhou, and they proved the following thing. This is a result for surfaces in R3. So take just a cylinder in R3, the round cylinder, and consider any C3 perturbation, right, from your cylinder, and then you start the Ricci flow from your perturbation. But they proved that, like, for sufficiently small C3 perturbations, the flow will basically develop neck pinch singularity in finite time. What does this mean, neck pinch singularity? I'm going to define later, but for now, you can just think that the singularity model is a cylinder here. That neck pinch singularity here means that the singularity happens in finite time, and when you rescale parabolically and take the limit, then that will converge to a round cylinder S1 cross R. Right? So we have even more results in the mean curvature flow. For example, Golding and Minkowski, it was like more than 10 years ago now, they proved, they introduced this notion of entropy, which is very much related to Huskins integral for the integral that Huskin introduced in the mean curvature flow. And they showed that all entropy stable shrinkers are the round spheres, Rn, which is the Euclidean space, or the generalized cylinders, Sk cross Rn minus k. So they can sort of classify all of them. And then the next question you can ask is the stability question. Can we also say something about the stability in this dynamical sense? And then recently there is a result of Chodosh, Mantoudillis, and Schulze, who also proved the result in R3 for surfaces. And they proved that the mean curvature flow of a generic surface M of 0 can encounter only spherical or cylindrical singularities, at least until multiplicity occurs for some tangent flow, right? So what does this mean? This means that, like, let's say that you don't have any multiplicities of the tangent flow, so that all singularity models come with multiplicity 1, then all what you can get are either spherical or cylindrical singularities, right? So all these singularity models that I mentioned here have to be either the round sphere or the round cylinder, okay? Not for every M of 0, but again, in the sense that I mentioned later, you start with something, m of 0, and if you flow it, and if you develop something else, which, if you actually reach the singularity, which is not a sphere or a cylinder, you can perturb your initial hypersurface, so that when you start flowing from the perturbed one, it will again develop a singularity in finite time, which will be modeled on either S2 or S1 cross R. Okay, so this is like what the result shows, but then it has been really improved. So this, so we can now erase this sentence at least until multiplicity occurs for some tangent flow, because very recently Baumler and Bruce Kleiner proved an amazing result. They proved the multiplicity one conjecture for the mean curvature flow for surfaces in R3, and they showed that any blow-up limit, right, has to have multiplicity 1, right? So this is like, so this means that in the, at least in these lower dimensions, generically all singularities are either the sphere or the cylinders, right? And you would like to have something like that in the Ricci flow. In the mean curvature flow, they could push it, but with some assumptions also to some higher dimensions, as far as I know. But in the Ricci flow, the problem is that like even the first step is missing, which would be stability in some linear sense, right? So calling Minicotes' result, it's not available for the Ricci flow. So then it's like it's much harder in that sense. Okay. So now, like I will just briefly mention this right work in progress, which is a joint work with Eisenberg, Danknop, and Ziluma. So here is okay, so here is first what I'm going to tell you. How you can, for example, construct a flow which develops a generalized cylinder, SK cross RP, as a singularity model, right? So you can start with, you see, you can start, so SK is just a round sphere, and this little r here, right? So this little r here just denotes the radius of the sphere. So start with a direct product of a sphere of a very small radius, and here you have a sphere of a very big radius, and use that as an initial data. And then the Ricci flow starting from something like that will develop SK cross R and minus K. Remember, we expect this to be somehow like generic singularities. So we want to push this a little bit further. We would like to have an open set of initial data which develops this kind of singularities. So we cannot do quite that, but we can go to this multiple warped product metrics. Right? And here I just remind you on this slide what they are. So B is the base, and these F1 up to Fa are the fibers. And each Fi is like Einstein with the Einstein constant mu A. Big N is the dimension of your manifold, and these Ba are the warping functions. And the result that I will state are for n is equal to 1 and n is equal to 2. And we are still working.
The connection's a little tough.
Oh, yes. Okay, you'll not touch them. Right, so what is our goal? Our goal is that you give me any PQ in N, and we want to construct an open set of initial data, but an open set within this work product structure, so that the Ricci flow starting at any of the metrics in the set develops SP cross RQ as a singularity model. Okay. Okay, so if you manage to do that, that speaks in a favor of this picture that I mentioned earlier. The generalized cylinders are basically expected to be stable and also sort of generic singularities in dynamical sense, as I mentioned also like what holds in the mean curvature flow, at least in R3. Okay, so here I define, I give you assumptions A1 to A3. And these assumptions basically they define the open set of initial data that we want to consider, right, on these multiple work product structures. And remember, VA are just the warping functions. And we have the assumption A1, which we call the single fiber pinching. And we just require that the minimum of this V squared of 0 divided by 2 mu A. Mu A is just the Einstein constant, is greater than V1 max squared at 0 over mu1, right? So for all A's from 2 to A. So this basically will ensure, as you will see later, that all fibers F2 up to Fa, right? That the only fiber basically which will pinch is the first fiber. The first fiber will pinch while the others will not. So when you blow up, the other fibers will give you RK factors in the blow up limit. Okay, so that's why it's called the single fiber pinching, because this just makes sure that the first fiber basically shrinks before the others do, right? So the singularity, and that's when the singularity happens. And then the assumption too, we need only when we work with a two-dimensional base. Okay, so here I introduce this quantity P, which is just the sum of Na, like the norm of gradient WA squared. Which is just the quantity defined in terms of the gradients of the warping function. And then F is just R check plus 2P. And what is this R check? This R check is just the scalar curvature of the base. Let's say when the base is two-dimensional, then the whole curvature is controlled by the scalar curvature. So everything is controlled by the scalar curvature in dimension 2. And we want to have some control on R check. And we want to achieve it by the maximum principle, but as you will see from the evolution equation, we cannot do it right away. So we had to add this term 2p, which helps us basically control the bad terms coming from the evolution equation. And what we required that at the initial time, right, this quantity f is sufficiently small, right? So which means that like you have like the scalar curvature of the base is not too big initially, okay? And then assumption 3, we need to prove that indeed you get type 1 singularity if you start with any metric satisfying assumptions A1 to A3. And for that, we either need that the scalar curvature of our manifold at the initial, so these are all assumptions at the initial time, is bigger or equal than 0. And I'm just going to tell you that the Ricci flow has the property that if this is greater or equal than 0 initially, it's preserved along the flow, right? So we either need this, or if that is not true, then we always have some lower bound on the scalar curvature, and then we need V1 to be smaller than some constant C1, which we compute in terms of this lower bound on the scalar curvature. So these assumptions A1, A2, and A3, as I said, hold only initially at time 0, and they describe the open set of initial data, right, to which we want to apply the Ricci flow and say that, the singularity that develops for all of them is type 1, and then maybe in some cases we can say more, that it has to be the generalized cylinder, okay? So here is the first theorem. I'm going to state it first for n is equal to 1, so which means that the base is one-dimensional. So we can show here that if you take any PQ in N, right, then we can find an open set of metrics on this M, which is the multiple warp product, right, where N2 up to NA, they sum to Q minus 1, and N1 is P, so that if I start the Ricci flow at any of these metrics, I can guarantee that the singularity that happens is of type 1, and that the singularity is actually modeled on one of those generalized cylinders as P cross RQ, right? So for any P and Q you give me, I can always hook up this manifold M, where F1 up to Fa can be any Einstein manifolds, compact, and right. So so you see, like here we have N2 plus up to Na is Q minus 1. And here we have like R, like Q R factors, right, in the limit. And that happens because like only like our assumption A1 ensures that this fiber pinches off. So what does this mean? This means that the V1 becomes 0 somewhere, like on the first fiber, before that happens for warping functions on all other fibers. So all other fibers somehow get some control. And when we blow up everything, then all of them, F2 up to Fa, right, will contribute to these RQ factors in the limit. So this is what I already said. Okay, and then the second theorem, I can state it for the two-dimensional base. Again, you have this multiple product structure, right, on your manifold M, and we can show that even in that case, that there exists an open set of matrix on M of this multiple product form, so that if you start the Ricci flow at any of these matrices, you always develop a type 1 singularity at some finite time. And then if you define these parabolic rescalings, right? So these rescalings that I have on the slide, these are the rescalings that you do in the case you have like type 1 singularity, right? So you just parabolically rescale the flow like this. And then we can show that for any sequence tau I going to infinity, right? This basically converges subsequentially to, see, RP cross KQ, right? Where KQ is a non-flat gradient shrinking Ricci soliton. So as I said, like as before, all these factors F2 to Fa, when you blow up, they will contribute to these flat factors here in RP. And then only from the base across the first fiber, you can basically get this KQ, which is like the, and so if you just count the dimensions, that's how like the dimensions above should relate with the dimensions in the limit, right? So KQ basically comes from the base cross Fn minus 1, F1, sorry. And so we can say that KQ is just a non-flat gradient shrinking Ricci soliton, but we would like to say that it is like also like a generalized cylinder. And for that, we come to the question if one can basically classify the shrinking Ricci solitons, which I have the, like, which look like this. So let's say that you have something that looks like this. But this is a working function. Let's say you have a fiber F, and let's say that the dimension of B is equal to 2. So the question is, like, if you just consider this, can we classify all gradient shrinking Ricci solitons, right, which have this working product structure, but over a two-dimensional base, right? Because if it's over one-dimensional base, this is very well understood. If it's over the two-dimensional base, it is not known yet. And I'm just going to say that if you consider Einstein matrix, right, that has been done, and either like then like the classification of such things is very well understood in the case of Einstein matrix. And Ricci solitons are the generalization of Einstein matrix. But in Ricci solitons, since you have this potential function f that gives you trouble, so it's still not known. So that's like okay, so like how do we achieve like these theorems B and C that I mentioned? Basically, we use the maximum principal arguments. And right, so what is assumption A1 here? I'm just going to remind you, assumption A1 just make sure that like the first fiber pinches off before all others do, right? So what does that mean? This means that V1 goes to 0 somewhere before others Vi go to 0, right? So this is like what assumption A1 is for. And by using this assumption A1, we exactly prove what I told you, that there exists some finite time t, right, and some constant delta bigger than 0, so that the minimum of V1 goes to 0 at this time, capital T, while the minimums of all other working functions are bounded from below by this constant delta, right, for all times up to this time, capital T. And then also like by very simple maximum principal argument, you can also prove this gradient bound on all working functions. Right? So this just comes immediately from the maximum principle. So now we want also to control the scalar curvature on the base, which is R check. So to do that, here I wrote like the equation for R check. So it's this one here. And let's say that you were just on the Ricci flow, right? If the base was just involving by the Ricci flow, right? Then you wouldn't have this third term here, right? So this R check T is Laplacian R plus R squared. It's just the evolution equation of the scalar curvature under the Ricci flow in 2 dimensions, right? But unfortunately, like we also have this term and also this term, which come from the fact that you have this working product structure, and you need to control the scalar curvature in order to control the Riemannian curvature, because you would like to say what happens at the singularity time. What my goal is to tell you is that at this singular time where this V1 goes to 0, basically the curvature has to blow up, and it has to blow up at a rate constant over capital T minus T. Right? So that is what I want to show. Right? And in order to do that, you have to control all these curvatures. And so now if you need to control our check, of course, if you are in the two-dimensional base, because if you are one-dimensional, then I mean, there's nothing to do something like that, and it's much simpler. But if it is in the case of a two-dimensional base, by using our assumptions and by using the maximum principle, you can prove this bound that I wrote, that our check is bounded by the maximum of some uniform constant and 2mu1 over this 3v1 squared. So you can see that if v1 goes somewhere to 0, then you lose the control on the scalar curvature of the base. And to show this bound on our check, right, as I told you earlier, we consider this quantity f, and we apply the maximum principle to this quantity, because the terms coming from the evolution of this term p basically help us control these bad terms that you have in the evolution of our check. Right? So yes, so that's why we want to consider the combination of them. And now remember, to control the full Riemannian curvature, you need to control the curvature on the base, which we just have by like our first estimate, right? But then you need also to control like the gradient terms, which we also have, because I told you that the gradients we can bound by the maximum principle on the previous slide, but you also need to control the Hessians of V, right? So to control the Hessians of V, we introduce this this quantity chi sub a, right, which is just the Hessian of the working function squared, and we introduce this quantity big F, right? And then we compute the evolution equation of this, where this b we choose later appropriately. And now, like in both cases, if it's no matter whether the base is one-dimensional or two-dimensional, right, you can compute the evolution equation for this f, and you get this, right, which implies that, right? So what does this tell you? This means that as long as V1 is bounded from below, everything is nice and bounded, right? So as long as V1 is bounded from below, all curvatures are bounded, and you can therefore continue the flow. But we know, right, that V1 has to go to 0 at some time capital T, right? So which means that most likely the singularity will happen there. Right, this is exactly what we show in this type 1 lemma, right? We says that if dimension is 1 or 2, and we have all our assumptions holding, then we already know there is a singular time capital T, and now I claim the singularity which occurs there is always type 1, right? So that means that all my flows are actually type 1 flows, so they satisfy this kind of bounds for the curvature, right? And this time capital T is exactly the one where the minimum of V1 goes to 0, right? So that's what I was saying, like the first fiber pinches off, while the others, no, they stay bounded away from 0. So to prove that it is like a type 1 flow, you need to establish an estimate like this. So the minimum of V1 is bounded from above and below, like this. Right? Because you see, like on the previous slide, so if you look at the control, right? So if you combine that type 1 lemma, right, together with this, right, then you will basically see that the Riemannian curvature is bounded by C over capital T minus T, where capital T is time exactly where V1 goes to 0. Okay. Right. So, and this upper bound is quite straightforward. Minimum V1 follows immediately from the maximum principle, and for the lower bound, you have to do a little bit more. You have to consider this quantity P, and then do some little tricks. Okay, which I will now skip due to lack of the time. I will just say that in the end, right, you establish this bound that we want. This, which means it's a type 1 flow So all the singularities are type 1, right? So which means that now you can perform this type 1 rescaling by capital T minus T, right? And since we have this bound here, if I perform this rescaling, then for the rescaled flow, the norm of the Riemannian curvature will be uniformly bounded. Once I know that the norm of the Riemannian curvature is uniformly bounded, because of the regularity properties of the Ricci flow, I can take the limit. And then see what the limit is. Right, so after taking this type 1 limit, we can basically show, as I said earlier, that the limit is of this form, right, qk cross rp. And by the results of Neighbor and Anders, Muller, and Topic, we know that this qk, that this kq has to be a non-flat gradient shrinking Ricci soliton, right? You can also prove that even in the limit after you go up, so this shrinking soliton has a working product structure, so it's a work product over a two-dimensional base. And now what we are lacking is the classification of those things, right? Which is known in the case of Einstein manifolds, but not yet in the case of shrinking Ricci solitons, which are the generalizations of those. Right, so. Right, our goal is basically now, next goal is to understand, right, this, to basically understand what this is, right? Okay, we know it's not like a gradient shrinking Ricci soliton, we know it is a work product over a two-dimensional base, but we want to understand more. So can we say that, like, at least because it comes as a blow-up of the Ricci flows, maybe we can say that it has to be a generalized cylinder. And maybe like in the last few minutes, I just want to briefly mention that third topic, which was the asymptotics of neck pinch singularities, right? So now we go back to the singularities which are modeled on a round cylinder, just Sn cross R. And here is the definition that we say that the flow develops a neck pinch singularity at p comma t if, right, when I rescale by, if I rescale this way, right, by capital T minus T, which is this parabolic rescaling, if this converges to a round cylinder, then we say that at P, capital T, we have a neck pinch singularity. And the first rigorous examples of this phenomena were constructed by Angen and Knopf. Basically what they did, right, they were considering rotationally symmetric case, and then they put two big spheres joined with a small neck, right, which is called a dumbbell, right? And what happens here, right, as you flow forward in time, right? So these spheres tend to shrink, but the neck also tends to shrink. But if you make neck much smaller than the spheres, the neck will shrink before the spheres disappear. So you will have basically a picture that looks like this. So you will have a neck pinch in the middle. And then if you zoom in, so what does zooming in mean? This means that if you rescale this way and take the limit, right here, what you will see is a round cylinder. Okay, so this is like, okay, so, and they basically so that for an open set of this initial data, which are rotationally symmetric, right, open set in the subset of rotationally symmetric metrics, right, they derived even the precise asymptotic behavior of this neck pinch phenomenon. So these examples that they have here are called non-degenerate neck pinches. And this is because no matter, like, because now we can even take the sequence of points, right? Pi, I can take the sequence of points Pi, where Ti converges to capital T, and I can rescale around those points by any lambda I going to plus infinity, right? And if every time the limit is this round cylinder, we call such a singularity non-degenerate. Right? But what can happen is also that if you take these spheres of the right size, if you take one sphere much larger, let's say, than the other one, something like that, right? Then if you run this by the flow, right, this sphere will shrink much later than this flow, than this sphere on the right. But you can make these sizes in such a way so that this neck and this little sphere shrink at the same time. So they disappear at the same time. So you develop some singularity here. And now this singularity is called degenerate neck pinch. Okay. So what does that mean? This means if I take some sequence of points pi, ti, for which ti converges to capital T, and if I rescale around those points, I may see a cylinder as a singularity model, but at the same time, I can come up with another sequence of points qi, si, which are somehow closer to this tip here, right? And like if I rescale them appropriately, I will see something which is a Bryant soliton, which is a steady soliton in the Ricci flow, which I haven't talked about, but they also exist and they also model the singularities. And this is like the example of this degenerate neck pinch, okay? And they are also rigorously constructed by Anken and Heisenberg and Knopf, and they even considered their asymptotics. And this is the example here is the example of type 1 singularity, and this example here is the example of a type 2 singularity, right? And these are expected to be generic and not these ones here. So now my student Hamid, he basically studied formation of neck pinches and their asymptotics in the rotationally symmetric setting. And he showed, at least in the asymptotic sense, the only possibilities which can happen in this non-degenerate case. Right? So here is let me briefly tell you just the setup. We can just consider rotationally symmetric metrics, right? So this G of T, rotationally symmetric. We even impose, let's say, reflection symmetry. All these symmetries are preserved along the Ricci flow. And then you introduce this S, right? Which is basically a geodesic distance between the orbit of at x and the equator, which is an SN orbit at x is equal to 0. Okay, and so here is the result that he shows that if you take like this mg of t, which is type 1 Ricci flow with some singular time capital T and has these symmetries, and let's assume that it only develops this type of neck pinch type of singularities. What does that mean? Like, okay, so this sentence that develops a neck pinch singularity, you can mathematically write in the following form, right? I take U to be, right, the rescaled radius. This is the rescaled radius of the original flow. It converges to 1 uniformly on this rescaled sigma. Sigma is also rescaled distance from the equator, and tau and time is also rescaled. And then what he shows is that only 1, 2, or 3 can happen, right, for any rotationally symmetric data. So either this rescaled radius converges to 1, 1 corresponds to the cylinder. U is equal to 1 just defines the rotationally symmetric cylinder. Converges to 1 like faster than any exponential, or U has these asymptotics here. Or like when m is greater or equal than 0, you have like these asymptotics that I wrote here, where this sigma 2 minus 2 and this h2m are just the Hermite polynomials, which correspond to the linearized operator of the Ricci flow around the cylinder, right, around the cylinder. So let me just make a comment here. So the first case, by the first case, I mean this faster than exponential case, it's unlikely to happen. You would expect that if one happens, namely if you have conversion to a cylinder at the rate which is faster than any exponential, that the solution itself must be a cylinder, which is not because we start with a compact initial data. So you would expect this to be ruled out, but we still don't know how. And why do you expect that? For example, Kochvar showed that if you have a Ricci flow solution, and that it has a compact shrinker as type 1 singularity model. For our case, it's a cylinder, which is non-compact, but it is a compact shrinker. And if there is a sequence, like along which rescalings converge faster than any exponential to that shrinker, then the solution itself must be this compact shrinker, right? So that's why we expect also the first case shouldn't happen, and that we should be able to prove something like Kochvar did for the compact shrinkers. But the problem is that argument in this Kochvar paper relies on Loyashevich inequality, right, which is satisfied by Perelman's functional. For example, in the mean curvature flow, Golding and Minicozzi proved like the analog of this Loyashevich inequality also in this for like when the singularity model is a cylinder, but this is not yet available in the Ricci flow. So the Ricci flow is also lacking there. So we cannot still prove. Okay. Maybe I'll just tell you some open problems. So here are the questions. Now if we precisely understand like how the singularity can form, at least in the rotationally symmetric Ricci flow, right? We have precise asymptotics. Let's say that we can rule out case one, which we still cannot. But like, right, this asymptotic behavior, as I said, is given by the eigenvectors of the linearized operator of the Ricci flow around the cylinder. And the question is, can we use, for example, this result for type 1 closed rotationally symmetric Ricci flows to prove that they can only have finitely many singularities, finitely many points at which the singularities happen. This result, analogous result like that in the mean curvature flow was proved by Altschuler, Angenen, and Giga. The next question that you can ask, if Sk cross Rn minus k is really dynamically stable, right? In the sense, for example, I mean, you can define that in the sense that you want, but for example, if you have like initial metrics, then you start flowing it, it develops this generalized cylinder as a singularity model. Can you then say that for a neighborhood of such metrics, when you flow any metric from that neighborhood, the same thing happens, that you still have Sk cross Rn minus k as a singularity model. The question that you should maybe answer before that is the question about linear stability, classifying linearly stable shrinking Ricci solitons, because you can define like a linear stability of shrinkage with respect to the second variation of Perelman's functional. And it is known that Sn and Cpn are linearly stable among the compact ones, right? But even to classify the compact linearly stable shrinkers in the Ricci flow, even that is not known, right? Even that is not known. So that's a problem. And then you remember that I gave you a result that the spheres and the cylinders are like the generic singularities in the case for the mean curvature flow when you flow surfaces in R3. So the analogous result would be something what happens for the Ricci flow in 4 dimensions, right? Because 3-dimensional Ricci flow is very well understood. But for example, can you prove that these generic singularity models in dimension 4 are those that I mentioned here that would be natural candidates based on works of others? That is far from known, because in order to answer that, you really first to answer a question like that and define maybe linear stability even of non-compact shrinkers and such. But as I said, even in the compact case, this is not known. So Ricci flow is a little bit behind the mean curvature flow in that sense. It's all stop here.
Okay. Any questions? Okay. Oh, okay.
In your definition of the type 1 singularity, is it just big O, or it doesn't have to be precisely asymptotic 1 over?
Yeah, it is, because it is known in the Ricci flow just by simple maximum argument that if the curvature blows up, right, the singular time has to be at least at the rate c over time.
Your upper and lower bounds.
Mm-hmm. Yeah. You always have, you cannot have better than t minus t. That's what I'm saying. You cannot have t minus t to 1/2. No. It has to be at least 1 over capital T minus t. But for type 1, it just means you have an upper bound. That's the only thing that you have here imposed.
Okay, again.
And I also had a question. In your definition of the weak stability,
Mm-hmm.
what norm was that?
That was
Is that
the
just
norm.
infinity norm?
Right, yes.
Same as all of the other?
Yeah.
Okay.
In case there are any questions, speak now. Otherwise, I'll let you all go to the cookies and the tea.